So a nice review paper came out on coastal carbon fluxes, and it's a nice review of the data, the processes, and also goes into future projections. The main points made in the abstract: a new synthesis yields an estimate for a globally integrated coastal ocean carbon sink of minus 0.25 petagram carbon per year, with almost 90% of that removal occurring in polar and subpolar regions. We'll see some maps in a minute. The sustained coastal and open ocean carbon sink is vital in mitigating climate change and meeting the targets set by the Paris Agreement. So we are looking at every little possibility of continued carbon uptake in the Earth system. Coastal carbons we have discussed in terms of blue carbon as well, where additional carbon sequestration is possible by restoring and preventing degradation of coastal ecosystems like mangroves, for example. Uncertainties in the future coastal ocean carbon cycle are associated with concurrent trends and changes in the land ocean atmosphere coupled system. The major gaps and challenges identified for current coastal ocean carbon research have important implications for climate and sustainability policies. This is obvious, and yet human activity at the coasts tend to be very high. Perturbations to the ecosystem, land ocean exchanges, and so on. Plus, the population is expected to continue to grow as well. So if you look at the schematic of the land, marginal seas, and the open ocean with the atmosphere sitting on top, you of course have the exchanges, CO2 exchanges and fluxes with the atmosphere. We always have to worry about whether coastal oceans as a whole remain a sink or a source, and whether they will continue to remain sinks if they are sinks now, or if they will become stronger sources if they are sources. So from land you get fluxes of dissolved inorganic carbon coming into the marginal sea, and that has a time variation and exchange with the open ocean. Within the marginal seas, of course, you have the biological pump, which has net ecosystem primary production, productivity, and net ecosystem calcification. And you have the marginal sea activities, which include reception of DIC, dissolved inorganic carbon, nitrate, phosphate, dissolved organic matter, and particulate organic matter. You have eastern and western boundary currents. You have eddies doing their thing in terms of exchanges with the atmosphere, supplying to the biological pump, and exchanging with the open ocean. And you have coastal upwellings, of course, and there is strong diapicnal mixing, which is basically mixing across the stratification, water mass conversions across density layers. There are outer plume exchanges, CO2 uptakes, degradation and remineralization of POM and calcium carbonate, production and rain happening, of course, and shelf break upwelling happens. And of course the open ocean has its own processes of DIC, DOM, nitrate, and phosphate, which exchange in this way. So often coastal regions and marginal seas have these estuarine or reversed estuarine circulations, where ocean waters tend to go in and fresher, lighter coastal waters tend to come out, and so on. So all these details matter. There is of course other details like the submarine ground discharge happening here. Hypoxia and ocean acidification are important, with eutrophication happening where blooms happen, often harmful algal blooms, which are not consumed at the surface because the zooplankton don't respond as fast when there is a huge bloom, rapid bloom, and that biomass sinks and gets consumed by anaerobic microbes, and they consume oxygen as well, producing hypoxia, and ocean acidification of course is an issue. Hypoxia is a big issue, resulting in all kinds of ecosystem damages, mortality of marine species that cannot run away, like shellfishes and so on. This is the updated air CO2 flux density in moles of carbon per meter squared per year in the global coastal oceans. So you can follow up the details in the supplemental material, but where it is blue colors, you have a sink, and where it is reddish colors, you have a source. So you can see that in the lower latitudes, mostly you have the coastal seas, coastal regions being sources to the atmosphere of CO2. So those are the flux densities in moles carbon per meter square per year, and some of the strongest outgassing happens here in the South China Sea, Indian region, and of course also South American regions, and on both sides of the South American regions. And of course there is a very complicated mix here of sources and sinks, which of course means there is not enough data to figure out whether as a whole these are sources or sinks. But high latitudes tend to indicate, polar oceans tend to indicate that they are mostly sinks, as we said in the abstract, and there are some strong sinks here as well. So a lot of the sink ocean carbon uptake in the coastal seas, coastal oceans, happens at polar, subpolar regions, with low latitudes mostly being sources. Here we are looking at the shelf area in millions of square kilometers, as well as 100,000 square kilometers, and you are also looking at spatially integrated CO2 fluxes. So they are sources or sinks, and flux density is shown here in mole carbon per meter squared per year. So you have eastern boundary currents which are taking up some carbon and have certain area. Western boundary currents occupy larger area and take up larger amounts of CO2. Indian Ocean as a whole seems to be a small source, but again, data may be an issue here. Subpolar regions are taking up large amounts, as you can see, with the CO2 flux density being here at order 2 mole carbon per meter square per year. Polar oceans are doing more work, taking up more of the CO2. Marginal seas take up a little, and tropics generally tend to be sources. Indian Ocean is a warm ocean, has lots of population density along the coast, so all those things matter in addition to the perturbations themselves, and how the ocean is also responding to the global warming dynamically and thermodynamically in terms of circulation changes and humidity and temperature changes in the atmosphere and the ocean as well. Looking at the meridional sections of annual CO2 flux density from one particular source, Rubert et al. Annual CO2 flux density obtained from compilation of data that is gleaned from the literature, and looking at the difference in PCO2 in the seawater and the atmosphere. Basically, if seawater is lower, then you are likely to be taking up CO2 from the atmosphere. If seawater has higher PCO2 than the atmosphere, you are likely to be outgassing, which is the eastern Pacific upwelling region being one of the strongest delta PCO2 regions, where one of the largest open ocean outgassing happens, for example. So this confirms what we saw before, that polar oceans and subtropics are generally negative here, so uptake by the ocean, coastal ocean, and lower latitudes are generally sources, but you can see that the uncertainties are high. So here you are near zero, but the uncertainty is quite high. Similarly here, uncertainties are reasonably high. Data also shows that the spread is quite large, but you still get the sense that polar oceans and subtropics are generally sinks and lower latitudes are sources, and delta PCO2 confirms that as well. Okay, just to give an example of the very region-specific processes, responses, and CO2 fluxes, you look at the northern Gotland seas, which is here between Germany, Sweden, Finland, Estonia, Latvia, and so on, part of the Baltic Sea. That's the station there. And you can see when you look at the PCO2 in microatmospheres over these observational periods going from about 2000 to basically very recent 2020, the amplitude or seasonal cycle is very high, and it is minimal in the boreal summer months because of the winds and the combination of things, and highest in PCO2 is highest in winter months, solubility high, cold temperatures, and so on. But there is a trend here in the air CCO2 PCO2, sea surface PCO2, and long-term trend in sea surface PCO2 is almost negligible here. But if you look at the mid-Atlantic bite off of North America, New York, then there is a much stronger trend both in the long-term sea surface PCO2 and the observed seasonality is much smaller than what is in the Northern Gotland Sea, and the air PCO2 also has a trend. So air PCO2 is increasing, of course, in all places because atmospheric PCO2 is increasing because of anthropogenic emissions, of course. And if you compare that to Southeastern Asia time series in the South China Sea, this is the Japan Sea, South China's northern end of the South China Sea. Scratch that, it's not Japan Sea, East China Sea, it's still the South China Sea. And you can see here there's not a lot of data, but indication is that it's a site where there is very little seasonality compared to these two sites, and there is a air PCO2 trend and also a sea surface PCO2 trend, and the seasonality here is stronger than here with whatever little data there is, and these peak the other way in the summer. The PCO2 is higher in the summer because of the warmer temperatures and winds and others. So you have to be aware of what the processes are. The review paper goes through lots of details of the processes with ocean dominated coastal seas and land dominated ocean coastal seas and so on. Looking at the pre-industrial processes of coastal carbon cycle and current periods, 20th century, 21st century, and future projections, you can learn quite a bit. So in the pre-industrial, we had 590 petagram carbon in the atmosphere. You divide by that 2, you get approximately the ppm in the atmosphere, around 280 or so. Primary production and respiration with land exchange and pools or reservoirs of carbon in vegetation, soil, and detritus. Weathering was the main uptake of CO2. Fossil fuels were there, but we hadn't started burning them like crazy yet. So weathering was also happening in the shelf area. Rivers were bringing in some fluxes. Coastal ocean was doing its thing, exchanging with the open ocean, and there were surface ocean and deep and intermediate ocean exchanges with their largest pool coming here in the deep ocean with a small flux that gets buried, because whatever gets buried here stays for a long. If you remember your residence time, you divide the reservoir by the flux, you get the residence time. So here it'll be like a couple of 100 million years, I think, if you can do the calculations. Okay, so we want to see, so here are the ocean exchanges. Again, small differences between uptake and outgassing between photosynthesis and exchanges, and that's what the net sequestration is. So we always have to worry about measuring them accurately enough to understand the small differences between what's going in and what's coming out. Okay, those are always difficult challenges. Looking at 2010 to 2020, here are the anthropogenic perturbations. You can see that we have used up a significant amount of fossil fuels over this period 2010 to 2020, just a decade, and we are emitting about 9.4 petagram carbon per year into the atmosphere. The atmosphere has jumped from 590 to over, what is that, 860 or so, and if you divide that by 2, you get 420 or so ppm that we are at. So land sink has started taking up more CO2. There is uncertainties, but that's the number. And land use change is emitting some, and of course we are also losing from vegetation, soil and detritus through deforestation, soil perturbation, warming, agricultural activities, and so on. So you can see that rivers are bringing in more DIC because of the land activities, agriculture, etc. Coastal oceans have more carbon in the pool now, and they are also sequestering maybe a little bit more, exchanging with the open ocean. So open ocean, deep ocean and intermediate ocean have increased their pool of carbon as well, and the exchange numbers are here. You can see the numbers compared to what was before in the coastal region and the open ocean region. So we have to be aware that these are just anthropogenic perturbations to the base numbers. Okay. Now projected 2050 to 2100, these are now after neutral years, which means somehow you have reached net zero with all these technological promises of carbon capture, sequestration, bioenergy, and so on. So we would have consumed more of the fossil fuels, will be emitting much less. We have somehow magically managed to reduce emissions from fossil fuels. Land sink has changed, land use change is still emitting reduced tiny bit, but land sink has also reduced because of various activities and policies and mitigation adaptation actions. And vegetation, soil and detritus, you can see the numbers here of what the perturbations, human activities are, and what the neutral carbon actions are for mitigation over land, and the changes in the marginal seas, coastal seas in terms of reservoirs and fluxes, and the open ocean reservoirs and deep ocean reservoirs as well. Okay, so obviously I'm not being very detailed about the numbers. You can go and read them. Each one carries uncertainties and they are estimates. Especially here you are taking future projections with all the scenarios, and in this period scenario uncertainties dominate, and then you have models with various levels of complexity, dynamic vegetation or prescribed vegetation, ocean carbon cycle differences in them, iron fertilization, calcification, etc. So lots of details are there in how these numbers are computed, and sometimes we don't even know, for example, the exchange between the coastal ocean and surface ocean, or how that will be perturbed after the neutral years in the future. Okay, so to summarize, rapid increases in ocean carbon observations have allowed further improvement in estimating the global coastal ocean CO2 sink and its spatial distribution. An updated compilation of air-sea CO2 fluxes based on observations reported in the literature shows that the global coastal ocean represents an integrated CO2 sink of minus 0.25 with uncertainty of plus minus 0.05 petagram carbon per year, with a global density of minus 0.68 plus minus 0.14 mole carbon per meter squared per year, confirming that the coastal ocean is an efficient CO2 sink. The strongest CO2 uptake occurs at high latitudes with combined contributions from polar, that's at minus 134 teragram carbon per year, and subpolar at minus 108 teragrams. So you have to be careful about teragrams and petagrams there, accounting for the majority of the global coastal carbon sink, as we said before. Moderate CO2 uptake with the highest seasonal dynamic ranges occur at mid-latitudes. Alternating uptake and outgassing of CO2 occur at low latitudes, as we saw in the South China Sea, for example. The latitudinal pattern in CO2 flux and its seasonality are controlled by both temperature and non-thermal factors such as water mass mixing and net primary production, characteristics of coastal ocean carbon cycling that differ from those in the open ocean. Okay. A framework based on river-dominated ocean margins and ocean-dominated ocean margin systems is used to conceptualize coastal ocean carbon cycle processes and provide a semi-quantitative diagnosis of individual coastal ocean systems. Application of this framework highlights differences in exchanges and boundary transport along the river estuary shelf ocean continuum and the intrinsic biogeochemical reactions that determine air-sea CO2 fluxes. Furthermore, a framework based on river-dominated margins and ocean-dominated margin ecosystems is used to conceptualize coastal ocean. Am I rereading it? Yeah. Okay, sorry about the screw up. Coastal ocean carbon models extending from conceptual or box models to three-dimensional coupled circulation biogeochemical models have been successfully implemented in a range of coastal ocean regions. These models simulate key processes, provide projections of future trends, and highlight uncertainties and challenges in our understanding of coastal carbon cycling. Global ocean biogeochemical models with improved spatial resolution allow simulation of important features and global trends in the global coastal ocean, such as coastal water residence times, air-sea CO2 exchange, and riverine fluxes. GOBEMs are also instrumental in simulating global trends in coastal carbon cycle processes and fluxes. Finally, observations and numerical model simulations are revealing long-term trends in ocean carbon fluxes, which have been perturbed since pre-industrial times. Anthropogenic alterations are anticipated to continue before and after net zero CO2 emissions, i.e. carbon neutrality, are reached, but considerable uncertainty is associated with impacts arising from concurrent changes in the land-ocean atmosphere coupled system. The observed differences in carbon fluxes and their long-term trends among different coastal systems indicate that physical and/or biogeochemical processes other than the abiotic atmospheric CO2 can be important controls on the evolution of air-sea CO2 exchanges in specific coastal ocean regions. Let's look at some future issues highlighted by the review. The ability to conceptualize and simulate future trends in the coastal ocean carbon cycle has been greatly advanced by improved understanding of spatio-temporal variability of carbon fluxes. This highlights the importance of continuing and enhancing ocean carbon observation programs that are coordinated with measurements of physical, chemical, and biological parameters that can be used to provide information that is responsive to regional interests, policies, and management. The continued development of global data products such as the Surface Ocean CO2 Atlas with improved coordination across the land-ocean continuum is critical to further advance understanding of ocean carbon dynamics. The observational systems often tend to be dominated by weather and climate forecasts and monitoring changes in anthropogenic impacts, but doing the measurements together for circulation, biological and solubility pumps are necessary for understanding the carbon cycle better and the continued response of the carbon cycle to anthropogenic perturbations, right? Regional models that fully couple the land-ocean continuum and global coastal ocean models that meaningfully resolve and reconcile coastal physical processes are equally important for the development of predictive capabilities at both regional and global scales. Predictive capability is increasingly needed to project the role of coastal ocean in the global carbon cycle and inform policies developed to achieve net zero carbon emissions by the mid-21st century. Here, improvements in data collection and advances in model structure and computational resources that allow integration of data and models are essential priorities. Improved representation of coastal processes through the use of conceptual frameworks such as the river-dominated and ocean-dominated margin systems provide an avenue to improve model skill and identify needed observations. So process understanding has to be advanced for advancing predictive understanding, but observations and observational based process understandings and fluxes and reservoirs are needed as well. Identification of a baseline condition representative of pre-industrial times is critical for assessing past effects of human activities and for projecting future trends in coastal oceans, carbon cycling, and air CO2 fluxes. Estimating this baseline condition and its associated uncertainty has important implications for advancing the ability to detect and quantify changes in the coastal ocean carbon cycle. Okay, so sorry about, I don't know why I did that. Sorry about that. As I said, this is just a brief introduction to the review, so please follow up with the nice paper if you want more details, and of course it has lots of very nice references as well. Sorry about this little mess up in the end. Okay.